Welcome to the Deep Dive, where you bring us fascinating material and we plunge right in to really extract the most important nuggets of knowledge and insight. Today, you've challenged us with a really compelling chapter from Robert M. Sapolsky's classic, Why Zebras Don't Get Ulcers. And we're focusing on an absolutely wild aspect of our own bodies, pain. Specifically, how, under just the right kind of stress, our minds and bodies can actually, well, turn off pain. Think about it. Have you ever twisted an ankle in the heat of a game, maybe, only to realize the severity of the pain much later, once the adrenaline faded? Or perhaps you've heard those incredible stories, people performing superhuman feats while severely injured, seemingly, well, oblivious to the pain. That phenomena, known as stress-induced analgesia, or SIA, that's what we're here to unpack today. Our mission is to walk you through this chapter, step by step. We'll start with the fundamental paradox of why we even feel pain. Seems odd, right? Then we'll journey into the intricate neurological pathways that process it, and finally arrive at the amazing discovery of our body's own natural painkillers and how stress mobilizes them. We'll explore the science, the real-world examples Sapolsky shares, and what it all means for you, all delivered in clear, engaging language designed for you to follow without visuals. Okay, let's unpack this. To kick things off, let's confront a fundamental question that I think most of us have asked at some point. Why on earth do we even have pain? It seems at times like such a cruel and, well, unnecessary system. Sapolsky starts his chapter with a fantastic anecdote from Joseph Heller's Catch-22. The character Yossarian passionately rails against the very concept of pain, wondering why a benevolent creator would include such a thing. He even suggests a system of blue and red neon tubes right in the middle of each person's forehead as a much better warning system than, say, the agony of a stomach ache. It's such a visceral human reaction, isn't it, to question pain's purpose? But from an evolutionary perspective, what is the undeniable utility of this unpleasant sensation?
It's an excellent point. Yeah, and that Catch-22 anecdote perfectly encapsulates our frustration with pain. Really does. But what's truly fascinating here is that despite its immense unpleasantness, pain is an incredibly useful and even indispensable tool from an evolutionary standpoint. It acts as a vital warning system, basically a biological alarm bell designed to protect us. Imagine for a moment an early human ancestor. Pain tells them if they're too close to a fire, right? Or if they've consumed something toxic and should stop immediately. It discourages them from putting weight on an injured limb, allowing it to heal without further damage. That's crucial. Even in our modern lives, pain often signals that we need to see a doctor before a problem becomes, well, irreversible. It's a feedback loop, telling our bodies, hey, something isn't right here, pay attention.
So it's not just a sensation, it's a built-in alert and repair system.
Okay.
Okay? But if that's its purpose, what happens if you don't have it? What are the consequences of living without that alarm?
Precisely. And this is where it gets quite serious. The chapter vividly highlights a rare and frankly terrifying condition called congenital insensitivity to pain, or simply analgesia. Individuals born with this condition can suffer severe, often unnoticed injuries. It's hard to imagine. Their feet may ulcerate because they don't feel the constant pressure of walking. Knee joints can disintegrate or long bones crack, simply because they don't know how much force to apply when moving or, how much strain a joint can handle. They can burn themselves without awareness, and some have even lost fingers or toes without ever knowing the initial injury occurred. Wow. This truly underscores the profound and protective role of pain. Without it, our bodies would simply fall apart from everyday wear and tear.
Yeah. That's a stark and sobering reminder of its utility. So pain is incredibly useful when it motivates us to change our behavior, to avoid or reduce whatever insult is causing it. But you also made a crucial distinction earlier, that it becomes useless and debilitating when there's nothing we can do about the underlying cause, like with a terminal illness. That framing of pain, not just as a sensation, but as an information system, is powerful. The challenge then becomes how we as humans adapt to pain when the information it's giving us isn't actionable.
Exactly. When the information serves a purpose, pull your hand away from that hot stove, it's beneficial, clearly. But when it's constant, unavoidable, and without a clear action to fix it, like the relentless pain of a chronic condition or a late-stage disease, it shifts. It goes from being a protective mechanism to a source of immense suffering. That's where the paradox truly lies, and where the body's ability to modulate pain becomes even more fascinating.
Which brings us to the next logical step. So we understand why pain is important, but how does it actually work? What's the physiological wiring diagram behind that sharp jab or that dull, throbbing ache we feel?
Okay, so the sensation of pain begins right at the very edges of our body, with specialized sensory receptors called nociceptors.
Nociceptors, right.
Yeah, these are tiny nerve endings distributed throughout our body, some deep within tissues, informing us about muscle aches or swollen joints, and others closer to the surface in our skin, detecting cuts, burns, or punctures. When you cut yourself, for instance, microscopic cells spell out various chemical messengers, things like histamine and prostaglandins. You've probably heard of those.
Uh-huh.
These chemicals then act like keys, basically, fitting into locks on those pain receptors, triggering them into action. Once triggered, these pain signals travel up dedicated nerve fibers, like tiny electrical wires, all the way to your spinal cord.
Okay.
There, they converge and funnel their information to specific neurons. Sapolsky refers to a central one as neuron X.
Neuron X, got it.
Think of neuron X as the primary relay station, a gatekeeper that receives the raw pain information from the body and then decides whether and how intensely to send that signal further up to your brain.
So neuron X tells the brain something painful happened, and then another part of the brain figures out where it happened. But it's not just a straightforward information highway to the brain, is it? There's that rapid, almost instantaneous reflex involved, which is kind of distinct from the conscious experience of pain, right?
Absolutely. That's a key distinction. If you stomp on a tack, a very rapid, ancient part of the system, mostly based in the spinal cord itself, affects the reflex withdrawal. You pull your foot away before your brain has fully processed the pain or consciously registered its unpleasantness. It's immediate protective.
Yeah, that happens so fast.
Simultaneously, other brain regions activate the broader stress response, signaling your adrenal glands, speeding up your heart, making you sweat, preparing your body for a potential threat. It's a layered response, both instantaneous and sustained.
Okay, so it's not just a simple on-off switch or a straight shot to the brain. What truly complicates and I think fascinates the picture is how that signal can be influenced before it even fully reaches our conscious awareness. Can you explain how the intensity of a pain signal can be so heavily modulated, even at the spinal cord level?
Right, this is where it gets really clever. That's where the brilliance of the system lies. And Sapolsky introduces an elegant model by pain physiologists Patrick Wall and Ronald Melzack. It's often called the gate control theory,
Gate control theory, okay.
and it helps explain this modulation. So pain fibers aren't all the same. There are fast fibers, imagine thin, insulated wires that carry information about sharp, sudden, immediate pain like a pinprick. And then there are slow fibers, thicker, uninsulated wires that transmit information about dull, throbbing, constant pain like a sustained burn.
Fast and slow fibers. Makes sense.
The key to modulation happens in the spinal cord. As we mentioned, neuron X relays pain. But crucially, there's also a local interneuron in the spinal cord called neuron Y. Yes, and neuron Y, when it's stimulated, inhibits neuron X. Think of neuron Y as a dimmer switch, maybe, or even a bouncer at the gate to the brain.
Okay, an inhibitor.
Exactly.
Yeah.
This specific setup explains a lot of our pain experience, so for sudden sharp pain. When those fast fibers are activated, say by stepping on that tack again, they stimulate both neuron X, the pain relay, and interneuron Y, the inhibitor. Both. Neuron Y is strongly stimulated, but neuron X gets a brief head start, sending a quick, sharp signal to the brain before Y's inhibition fully kicks in. So you feel that immediate, acute, localized pain.
Right, the ouch moment.
The ouch moment, exactly. Now, for dull, throbbing pain, with prolonged, diffuse pain from slow fibers, both X and Y are still stimulated, but Y's inhibitory effect on X is much weaker. This allows neuron X to continue sending a more sustained stream of pain signals, resulting in that prolonged, diffuse throbbing pain, like from a bad burn or really sore muscles.
That makes so much sense. And it explains why rubbing a stubbed toe or even a vigorous massage on sore muscles might dull the pain.
Activating those fast fibers, right?
Yeah.
Exactly.
Which in turn stimulates neuron Y more strongly, thus inhibiting the chronic pain signals from neuron X. It's like distracting the bouncer at the gate.
Precisely. You got it.
All right.
And it gets even more complex and powerful because the brain itself isn't just a passive receiver. It can send its own signals, called descending projections, all the way down to neuron X in the spinal cord, actively modulating its sensitivity.
Descending projections from the brain down.
Yeah, imagine the brain as a central command center with the power to tell neuron X, hey, dial down the volume on those incoming signals, or conversely, turn it up. If you're stressed and terrified in a dentist chair, for example, those descending projections can make neuron X really jumpy, intensifying the pain you feel.
Oh, great.
But on the flip side, if you're distracted or thinking positive thoughts or feeling safe, those same projections can make neuron X much less responsive to incoming pain signals, effectively turning down the volume.
This brings us right to the core of our deep dive. Stress-induced analgesia, SIA. This amazing phenomenon where under the right kind of extreme stress, you literally don't feel pain. So, what does this all mean for our perception of pain, and how exactly does stress make our pain vanish?
The descending projections from the brain that we just discussed are absolutely key here. They're central. Sapolsky provides some really compelling historical examples. Consider Henry Beecher's World War II study. He found that for injuries of similar severity, a staggering 80% of civilians requested painkillers, but only about a third of soldiers did.
Only a third, wow.
Yeah. The sheer stress of battle, the relief maybe of being wounded and removed from combat, it seemed to override their pain. And even earlier, the French physician Dupuytren observed a similar pattern over a century before, noting that for a wounded soldier, the news of an injury could almost be a relief they might be out of the battle, and this psychological relief was often accompanied by reduced pain perception.
And it's not just battlefield heroes either. Most of us experience this in more mundane everyday life, even if we don't realize it at the time. Think about getting completely absorbed in a sporting event and ignoring an injury, or pushing through an intense workout where the initial pain gives way to a kind of euphoria. That's SIA at work, taking over. The runner's high is a classic example that many of us can relate to. You hit a certain point, and the discomfort just, well, it fades.
Exactly. This is a
Yeah.
perfect example. And this isn't just mind over matter or psychosomatic in some dismissive sense.
Yeah.
It's a concrete, measurable, physiological phenomenon. Evidence comes from rigorous laboratory settings, too. Sapolsky describes the hot plate test with rats.
Okay.
When a rat is placed on a hot plate, it will quickly pick up its foot due to discomfort. Standard reaction. But if that rat is first put under stress, maybe forced to swim, or placed with a threatening rat, it will take significantly longer to react to the heat.
So the stress delays the pain reaction.
Significantly delays it. That's clear, verifiable, stress-induced analgesia. The animal's body has actively suppressed the pain signal because of the more pressing, immediate stressor. Survival first.
So the body's priority shifts from local injury to immediate survival. Makes sense. But the real breakthrough, however, comes in understanding the neurochemistry behind this incredible ability. Because on the face of it, why would our brains evolve to have such specific receptors for a plant compound like opium? It almost seems too coincidental. What was the aha moment that led scientists to the real explanation?
That's the eureka moment in the story. You're right, it seemed very odd.
Wow.
In the early 1970s, neurochemists made this huge breakthrough. They discovered specific opiate receptors densely distributed in the brain, particularly in areas involved in processing pain.
Opiate receptors.
Yes, they found that recreational drugs derived from poppy plants, like morphine, heroin, and opium, bind tightly to these receptors. This is how these drugs block pain by activating those same descending pathways we just discussed, effectively blunting neuron X's sensitivity to incoming pain signals.
Right.
But, as you rightly asked, why would our brains have receptors just waiting for compounds from poppy plants? This led scientists to realize there must be endogenous compounds.
Endogenous, meaning made inside.
Exactly. Made by our own bodies that
Yeah.
are structurally similar to these plant-derived opiates. These natural painkillers were named opioids. They come in three main classes: enkephalins, dynorphins, and the most famous, endorphins, which is actually a contraction of endogenous morphines.
Endogenous morphines, endorphins. Got it.
It's important to distinguish. Opiates are exogenous, coming from outside, like plants. Opioids are endogenous, manufactured by the body itself. These endogenous opioids bind to the same receptors, effectively inhibiting pain perception, our own internal painkillers.
So our bodies produce their own morphine-like substances. That's incredible. And this research even shed light on other mysterious phenomena like how acupuncture might work. That's often been viewed with skepticism by Western medicine.
Yes, exactly. It provided a potential mechanism. It was found that acupuncture, the traditional Chinese medicinal practice, seems to stimulate the release of significant quantities of these endogenous opioids. The best demonstration of this is using naloxone. Naloxone is a synthetic compound that acts as an opioid antagonist.
An antagonist, so it blocks them.
Precisely. An antagonist essentially binds to the opioid receptors but doesn't activate them. Instead, it blocks our natural opioids, our endorphins, from binding and doing their job. So, if naloxone is given, it blocks the pain-relieving effects of acupuncture. Its effectiveness is significantly dulled.
Wow.
This provided strong physiological evidence for acupuncture's pain-reducing effects, suggesting they are mediated, at least in part, by our own internal pharmacy.
That's a powerful validation. So we have these natural painkillers, these opioids. But how does stress specifically trigger this complex system? What's the link that activates this internal pharmacy in moments of duress?
Great question. In 1977, Roger Gilliman, who'd actually just won a Nobel Prize for other discoveries, demonstrated the direct link. He showed that acute stress causes the release of beta-endorphin, a potent type of endorphin, from the pituitary gland right into the bloodstream.
Beta-endorphin.
Yes, this is precisely why you hear about the runner's high. During prolonged, intense exercise, especially after about 30 minutes or so, this beta-endorphin builds up in the bloodstream, causing a widespread sense of analgesia and sometimes even euphoria. Other opioids, like enkephalins, are also mobilized within the brain and spinal cord itself, working directly at the spinal cord and via those descending pathways to shut off neuron X.
So it's a system-wide response triggered by stress.
It really is. And it's not just exercise. Many other acute stressors produce similar effects. The intense physiological stress of surgery, dangerously low blood sugar, extreme cold, high-stakes exams, even spinal taps, and especially childbirth. It's a powerful, evolutionarily conserved natural survival mechanism. It's designed to allow us to escape a threat, even if we're injured, basically postponing the pain until we're safe.
It sounds like a truly wonderful, finely tuned system, particularly for that zebra needing to escape a lion even while injured. That makes perfect sense. But previous deep dives have shown us that chronic stress responses often come with significant downsides, leading to illness and wear and tear on the body. This system, with its powerful opioid release, almost seems too good to be true in that context. Does chronic stress make you, like an endogenous opioid addict, or cause you to lose the ability to feel useful pain? It almost seems counterintuitive that a powerful natural painkiller wouldn't lead to some kind of dependence or burnout. Why does this system seem to be an exception?
That's a critical question, and it really highlights a unique aspect of stress-induced analgesia. In many physiological systems, you're right, chronic activation of the stress response is what ultimately makes us sick. It's the very core of Sapolsky's broader work, the reason zebras don't get ulcers. However, the chapter points out that opioid release is actually a remarkable exception to this rule. Chronic stress-induced analgesia doesn't seem to persist forever, and there's really no evidence that chronic, excessive endogenous opioid release leads to a stress-related disease, permanent addiction, or a long-term inability to detect useful pain.
Really?
Yeah, the system simply doesn't become permanently out of business or desensitized in the same way other stress systems might. It seems quite resilient in that regard.
That is a surprising piece of good news, then, from the perspective of stress-related diseases, one less thing to worry about in the long run, maybe. The body seems to have evolved a way to use this powerful tool acutely without incurring a massive physiological debt later on.
Indeed. It seems so. It's a testament to the evolutionary fine-tuning for immediate threat and survival, designed to kick in, do its job, and then largely reset. However, if we connect this to the bigger picture, for individuals facing real, unavoidable physical stressors, like someone agonizing through terminal cancer, or a soldier badly injured in combat who will eventually leave the battlefield, the temporary nature of this profound analgesia means that the pain eventually and inevitably returns. The system is designed for a sprint, not a marathon of suffering.
That's a very important point. What an incredible deep dive into the paradox of pain and our body's amazing capacity for stress-induced analgesia. We've journeyed from Joseph Heller's philosophical frustration with pain to its undeniable evolutionary utility. We explored the intricate wiring of our pain pathways, those fast and slow fibers, neuron X and neuron Y, the whole gate control idea. And finally, the astonishing discovery of our internal pharmacy, those endogenous opioids like endorphins that can temporarily silence that critical alarm system under duress. It's a testament to the complex, adaptive, and truly awe-inspiring nature of our physiology. It really is. So next time you're pushing through a tough workout, maybe experiencing that runner's high, or just reflecting on a moment where you didn't feel an injury until later, you'll know the incredible life-saving science at play, all happening silently within your own body.
Absolutely. And while this capacity for temporary pain suppression is an unparalleled gift for immediate survival, especially in the face of acute danger, it also leaves us with a rather poignant thought. For those facing relentless, inescapable physical pain day in and day out, this temporary reprieve, while powerful in the moment, starkly highlights the persistent challenge of human suffering. Our natural systems aren't always equipped to permanently resolve that kind of pain.
A very sobering but important final thought. Thank you for bringing us this fascinating chapter from Sapolsky, and for joining us on this deep dive into the marvels and mysteries of pain. We hope you found these insights as compelling and thought-provoking as we did. Until next time, keep exploring, keep learning.